Hi students, welcome back to geology. Today we are going to be talking about mass wasting. All right, so mass wasting is kind of a blanket term that covers landslides, rockfalls, debris flows, any movement of material down slope. Doesn't matter how the movement is moving or how the material is moving or what type of material it is. As long as it's being moved due to gravity, it's considered mass wasting. A lot of the times we use the term landslide as kind of the blanket term, and I will do that a little bit, but technically our blanket term is going to be mass wasting, and then a landslide is specific to mass wasting. All right, so why is it important to learn about mass wasting? Why does it matter? We need to learn a little bit about mass wasting and how these materials are moving, because they do threaten lives, homes, businesses. They can cause a lot of damage, and that can cost a lot of money. So there's an average of 25 to 50 deaths per year, and that's not necessarily an insignificant number. That number could increase very quickly with one rockfall, one landslide at the wrong place at the wrong time. And so we really want to be able to mitigate damage. And then it does cost about $2 billion a year in the United States to deal with landslides. So the biggest factor here is not necessarily the number of deaths, but the amount of money it's going to cost to mitigate and or repair anything that has been damaged. So technically they do more damage than earthquakes, volcanoes, tornadoes combined, but not necessarily hurricanes. So hurricanes and floods do more damage. Water is much more damaging than movement of material. And the yearly losses are increasing, and that is because of inflation, right? So not only do we have inflation, but we're also building in a lot more rural areas than we used to. So because we have more roads and because we have more people are going to be on these slopes that are not necessarily super stable, or they've been overcut or undercut, and now they are no longer holding up all of that material. So the United States Geological Survey has an inventory of landslides. This orange link down in the right-hand corner, you can click on in your PDF version of this presentation. And it will take you to this website that will show you all of the different landslides. You can click on them and learn information about different ones. So if you're interested in a particular area, you can zoom in, click on them. But you'll notice that most of the landslides are going to be where you have some sort of relief, where there's some sort of slope, right? So because mass wasting occurs where material is moving down slope, there has to be some sort of slope there in order for material to move. So in Fresno, we don't necessarily see that many landslides, but in the neighboring mountain ranges, the coast ranges, and the Sierra Nevada, we definitely do. So looking at California specifically, here's a look at some of our hazards for landslides, and you can tell that most of it is along the coast. What is one of the big things that runs along the west coast of California? The San Andreas Fault, right? So when the ground shakes, do you think material is going to stay on the slope? Not if it's got a weak point. So that material is going to come down. The other reason we have a lot of landslides along the coast is because we have coastal erosion as well. So coastal erosion, waves hitting and crashing against the cliff faces, is going to weaken the cliffs, and it's going to technically fall down slope, which would technically be a landslide or some sort of mass wasting. So looking at the anatomy of a typical landslide, this is generally what you would see. The first thing you'll notice is probably a main scarp, which is going to be where material first started to slide down, and it exposes a bunch of fresh rock or fresh soil. And then you'll have a crown above that where there are some cracks. Then you'll get into the main body. You might have a minor scarp between the main scarp and the body. And then the other big part that we do see is the toe, which is the terminus of the landslide or the end of the landslide. And that toe is really important to understand when we are doing mitigation or cleanup, because if that toe is removed without buttressing the rest of the material is going to continue to fall, right? So that toe is kind of like the stopping point for the landslide. It's holding everything else up that hasn't fallen further. So if you remove that without trying to buttress or brace the rest of the slide, all of that material will just keep coming down. And when we get to case studies, I'll talk a little bit more about how that would come into play when you're actually trying to fix a landslide. So landslides are classified by the type of movement and the type of material. So the first thing we look at there on the left is the type of the movement. Is it a fall, a topple, a slide, a lateral spread, a flow, or is it a combination? There are a lot of slides that I've seen that are, or mass wasting that I've seen that is very complex, and there are two different components. One of the ones we look at in Yosemite later on I will describe two different types of movements with that one as well. And it really just depends on what's happening with the slope and how the material is moving. And the type of material, we see either bedrock or some sort of engineered soils. So engineering soils are going to be just earth or debris. If it's debris, it generally has a very large range of material involved. A lot of it is coarse, but there can be some fines. And then with your earth that's there, like an earth fall, an earth topple, those are all going to be mostly finer materials. So we're looking at sand or finer, so sand, silt, or clay material. And it tends to move as kind of a cohesive unit. Whereas if it's bedrock, there's a lot of different pieces of rock that come tumbling down the mountain. So those aren't necessarily going to be cohesive. And then with your debris flows or your debris falls, a lot of the time those are driven by water as well. And so they tend to be fairly cohesive. And then one other note to point out, the slides, there is a rotational and a translational. So this depends on how the base of the slide is. Is it flat or does it have a curve? So in the Landslide Anatomy that I just showed you, that one has a curved surface. So that's a rotational slide. So the slide would kind of rotate as it comes down slope. With a translational slide, it's just going to slide on a flat planar surface. Okay, so that's the difference between the rotational and the translational. All right, looking at falls. So this is an example of a rock fall in Yosemite. And a fall starts with some sort of detachment of the soil or rock above a valley floor or on some sort of steep slope. Generally, we have a lot of relief, and so we're looking at something that's really steep, and it has the ability to free fall off of that cliff. And if it's not super steep, we're not necessarily going to see a lot of falls. So in Yosemite Valley, there's a lot of falls because the valley walls are really steep, right? And so we generally see a lot of rock falls and rock avalanches in this area. And so all of the material that comes from a fall will land at the bottom of the slope, and all of the material that collects the bottom of a slope from a rock fall, we call talus. We call it a talus pile. Topples are similar, but for the most part, we just have a forward rotation. So instead of rocks detaching and just free falling, we have kind of a vertical segment of rock that will detach and have a forward rotation and just kind of fall flat. So there is technically a free fall component, but in general, we're looking at some vertical component, vertical rock that detaches from the main rock and just kind of topples over. So this is common in basalt that is columnar basalt. So this is Devil's Postpile. So a lot of the big columns of rock that are vertical will detach from the face and then just kind of topple over and land in the talus pile at the bottom of the slope. So some of the other things that can contribute to falls and topples, this would be definitely stream erosion, or glacial erosion can also contribute. So anything that's going to incise steeper cliff faces, that's going to lead to more falls and topples. And on here, I have a bunch of lines running through the rock. Do you know what those are? You remember from erosion and unloading and things like that, those are joints. So those are cracks in the rock. And so the more cracks that are in the rocks, the more likely it's going to fail. Moving on to slides. This is a downslope movement of soil or rock that is generally fairly cohesive. And so it stays as one mass and it slides all together. They can be extremely slow to pretty quick. So sometimes, if you ever watch landslide videos, I've watched a lot of them. I'll link a few of them in your module. A lot of times you'll see like, oh, it just kind of slides really slow, and then maybe it catches some speed or some momentum and it starts going really fast. And then other times it just comes down all at once and you're like, what happened? So a lot of these are driven by rainfall, and we'll talk about more triggers in a little bit. And like I said, we have translational and rotational. The difference is just the slide surface. So translational is flat and rotational is curved. Is curved. Okay. All right, then we get into lateral spreads, which are not necessarily as dangerous, but they can cause a lot of damage, especially if they happen below a building. So this is when cohesive soil starts to expand, and this can happen when things like clay gets oversaturated. There's a particular type of clay, which we have a little bit of it in the Central Valley. It's called a fat clay. And when it's hydrated or overhydrated, it expands like a lot. And when that happens, it can spread the material out, and it usually does it in a lateral fashion. And so this can cause a lot of damage to homes and other buildings. All right, and our last one here is a flow. So this is when we generally have a fluid involved, a lot of it. So a lot of water. So we have some water here pulling down. You can see it's kind of dirty looking. So this is going to have some coarse material and some fine material. And during debris flows, unfortunately, they do also pick up a lot of other stuff. So they can pick up giant boulders that are sitting and are mobilized by that water. It can pick up tree branches and all kinds of other junk that happens to be in the way. And generally they follow an existing stream channel. And a lot of these are actually driven by wildfires, which a lot of people don't realize. But wildfires actually ruin vegetation, obviously, and it's removed. And then when heavy rainfall ensues, you end up with a bunch of loose material that can easily move down slope with that water. And so instead of the water infiltrating into the ground, like we learned with water, the vegetation's not there to support that. So the material just moves down slope, the water moves down slope, and it takes a lot of stuff with it. And this can be one of the most damaging, because if it goes into a low-lying area and floods it, we also have a flood problem, right? And so we don't want that in these cases. So when we do see fires, we try to do some flow mitigation so that we hopefully don't see a lot of it when we do get rain. All right, looking at some triggers. I know there's a lot on here, but it's just pretty face value. So we do have water saturation. So anytime the soil or the sediment becomes more saturated with water, this can come in a lot of different ways. You're going to have landslides. Like, it's just a given. Something's going to move. Something's not going to be stable. And so this could be water level changes. This could be from irrigation, snow melt, obviously rainfall. Rainfall is our most common. And then we do see shaking. So this could be natural or human activity. So this can come from volcanic eruptions, earthquakes, come from blasting from construction. We can also see meteorite impacts, but those are very rare. And then we also have undercutting and oversteepening, which also could be natural or from humans. And so if it's natural, we're looking at like stream undercutting or waves. Remember I was talking about the ocean waves hitting the cliffs that undercuts the material, and things tend to fail. And then obviously human activity. So when we build roads, they have to be very, very considerate of the slope that they are creating. So if they oversteepen the slope from its existing, you're going to have material come down onto the roadway like you see in this photo here. Also, lack of vegetation and wildfires, we've already kind of talked about. When there's no vegetation, the water isn't infiltrating into the ground, and so instead it's running off and trying to move material downslope, which we don't want either. And then, of course, landslides do happen without any known triggers, and you can't necessarily always predict them. So while we do know that rainfall is the number one trigger for landslides, we don't necessarily have the ability to say that this particular slope is going to move next time it rains. It could or it could not, depending on the conditions, right? And then, like I said, we can see bright sunny days where you might see a rock fall in Yosemite, and that has happened many times. We do try to mitigate everything, though. So depending on the type of movement, we do have different mitigation measures that we use. So for example, falls and topples, a lot of rock curtains are really common. So that bottom left there, you can kind of see a curtain over the slope. Those are really common along I-5 if you drive through like the Grapevine to Southern California. We also see retaining walls, which is the next one on the left, where it's kind of bowing outward. So the retaining wall is also used for slides too. And then we can remove it, or we can use rock bolts or shear pins. And so rock bolts and shear pins are the middle right, where they're installing basically bolts to try to keep, if there's a joint or a fracture, it's supposed to run through that joint and bolt it into the other rock that it's trying to separate from. And so sometimes that works, but that is a very extensive mitigation and expensive mitigation measure for falls and topples. And then, of course, we have rock sheds, which is the upper left, which is one of the most common for material that just will not stop. So along Highway 1, that's the one that's installed along Highway 1 in the Central Coast. And it is preventing serpentine from sliding down any further. And if it does, it just lands on top of the rock shed and can fall over it and into the ocean if it sees fit. So cars can continue to pass by and the road is not damaged. And then we'll look at another one that's a little bit closer to home. Then we also have slides. So we have lateral drains that we install for slides. That's the bottom right. And that helps take any water that did not infiltrate, puts it onto concrete and takes it downslope. And so instead of the material going with the water, it stays in these lateral drains and then it kind of dewaters the slope. We can also do that for spreads and flows. One of the more common that we see for flows is a debris catchment net, which is that top right. And so what that does is it holds back all of the material, but it lets water come through. And so the water can go through, but it holds back all that stuff that if a giant boulder came coming down the mountain and hit your house, like it's going to destroy your house, right? And so that helps try to mitigate that a little bit. And so landslides do cost money. We've already talked about this a little bit, but there's direct costs and there's indirect costs. So with landslides, the direct costs are, of course, the repairs, the replacement, maintenance of the property, mitigation of the slides, all of that stuff once a slide has already occurred. So here's an example for you. There was a Utah slide in 1983 that cost 21 million cubic meter of debris to come down and $200 million in loss. And that was in 1983. So that was 40 years ago. And so if you think about what that would cost now, it would be a lot, right? And then we have indirect costs like loss of production, loss of tourism. So when Yosemite has a landslide and they have to close off an area, they obviously lose money off that. Loss of any tax revenue on property, additional mitigation measures that you have to apply, any effects on water quality. So if the water is damaged, it costs money to still have water provided to whoever lives in the area. And then obviously any injury, death, or psychological trauma ensued by the landslide. All right, we're going to go through a couple of case studies here. We're going to start with the Ferguson rock slide, which is on the way to Yosemite along Highway 140. This landslide has been a beast. So it first moved in 2006, and that is the Merced River at the bottom right there. And the material went into the river, and luckily we didn't see too much flooding downstream. The problem with landslides coming into a stream is a lot of times they create what we call a landslide dam, and they dam and back up the water until it finally breaches. And then when that occurs, there's going to be flooding downstream. And so luckily there wasn't too much of that occurred. But their material completely covered the road, and so they had to put in temporary bridges. And those temporary bridges have been used until today. So the rock shed that they have planned to put in place has not been finished. But the plan is to put a rock shed here, just like the Highway 1 I showed you. There's a picture there in the middle of the slide of their like artist rendition of what it would look like. Because as they started moving the material, originally, it just kept failing. And so that is an example of them trying to remove the toe of the landslide, and material keeps coming down. And so they are slowly but surely getting things put in place. And I haven't seen an estimated completion date yet, but hopefully soon, so that you don't have to do the bypass and waiting for the light. If you've ever gone that direction, it's a beautiful drive, but you do have to wait for the light to change so that you can go across the bridge and then go back across the bridge. All right, then moving into Yosemite, this is the Happy Isles Rockfall. This is not necessarily the only rockfall they've ever had. They've had many, but this is a really interesting one because it has a two movement component to it. So this happened in 1996. There were two separate falls. The source is in the middle at the top there, showing you all the way from A to, I think it goes to F, D, or is E on the far right there. So that shows you all of the rocks and the source, so where they came and where they traveled. So this was around 120 million kilograms of rock. It's a lot of material. It generated magnitude 2 earthquakes. So at the bottom right there are some earthquake records from this rockfall. And we also saw tornado force winds. So the right-hand side, that black and white photo of trees, you can see where the impact site is and the winds that just pushed and knocked over a bunch of really, really tall trees that had been there for years. You can see the dust in the upper right-hand corner that deposited on the campsite that was right below Happy Isles, or is right below Happy Isles. It's still there. And the main thing that I wanted to talk about here is that there is a component of slide and a component of fall. So the bottom left shows you the component of slide and then free fall. So the rocks first started sliding down that slope, and then they hit that prominent ledge and they start free falling to the bottom. And then they impact and cause this big wind and knocks over all those trees and then deposits a bunch of dust. Looking at the La Conchita landslides in 1995 and 2005. So these were very avoidable. So this material is Monterey Formation, which is a shale, siltstone, sandstone formation. And there's also the Pico Formation, which also has some siltstone, sandstone, mudstone. And so these are really fine materials, and they're fairly cohesive. And so they moved as a cohesive unit downslope as a slide. And so there were two of them that happened. The first one was in 1995. This followed a lot of rain, so 400 millimeters of rain in January. There's the rainfall graph there for you. The landslide began in March, and it moved in less than 10 minutes. So all that material in that middle photograph there moved in 10 minutes. So it's pretty quick when you think about the amount of material that can be moved that quickly. There was about 1 million cubic meters of material moved. 9 houses were destroyed with no fatalities in 1995, which was good. The problem was these are $1 million homes, so because they're on the Pacific Ocean in Southern California, so there was a lot of damage, cost them a lot of money. I didn't put the numbers on there, but this was a very avoidable scenario because nothing should have been built here. So if you look at that infrared or false color image on the top left, you can see a scarp at the top there. And that scarp shows you an old landslide prior to the development of the housing tract there. And so this is something that could have been avoided. And then, unfortunately, even after 1995 happened, we did not learn our lesson. We tried to put Band-Aids on it, and it didn't work. It happened again in 2005. So that top right corner there shows you the Band-Aid. That is a retention wall trying to hold material from the 1995 landslide back. And so this one occurred in 2005, again, following a very heavy rain. So 430 millimeters of rain, which was a record rainfall day for them. And we saw 200,000 cubic meters of material come down, 13 houses destroyed, and unfortunately in this one, there were 10 fatalities. So the moral of the story is make sure that you don't build at the bottom of a slope that clearly has old landslide. And I think Southern California, after these 2 slides, learned their lesson because there haven't been a lot of major slides since then that have done this amount of damage. And then the last one here that I will talk about is a little far from home, but it is one of the largest mining landslides that we've seen in history. And so this is the Copper Bingham Canyon mine, and this led to 2 landslides kind of back to back. They were about an hour and a half apart from each other, and it moved about 145 million tons of rock. And so you can see just about how much rock we've got. We've got in the upper right-hand corner there some of their trucks covered with debris. And to give you an idea of how large those trucks actually are, no, the photograph doesn't do it justice exactly, but there's a photograph next to a regular, like mid-size SUV, smaller SUV. And you can just see how large those trucks are. So you can imagine how much material actually came down. This did generate a 2.5 magnitude earthquake as well. Luckily, because it happened at night, nobody was there working. So there were no injuries or deaths, which is amazing. Because if that would have happened at 9 a.m. the next day, we would have had a very different story. Although it did change the mine entirely, and there were hundreds of millions of dollars in damage due to the operation. They had to re-step the slope and rebuttress everything, and they probably lost a lot of money on revenue and production. All right, so in summary, mass wasting comes in many different forms. We see rockfalls, debris flows, landslides, topples, spreads, and they all move under different conditions. Landslides have many probable triggers, but rainfall is the most common, and they can occur with no trigger. We do have mitigation measures to try to keep slopes in place, and in California, we have a lot of examples of landslides. I will catch you guys in the next video. Bye.